And so now we're going to go over a super complicated thing for integration. And this is a technique to be able to help you integrate something that's a little more complicated. And basically, substitution kind of works like the opposite of the chain rule. So remember how when we have the chain rule, when we do f of x, g of x, when we take the derivative, we get f prime of g of x times g prime of x. And so we're going to want to try to reverse this, right? And so that's the goal of substitution. And so this is the first method of integration that you're going to see. You're going to see significantly more of these in 1014. But we're going to start looking at this one in particular because this one takes a while for the brain to grasp. And so it's good for you to start seeing it now and then revisiting it when classes start up again, whenever that may be. And so basically what we're going to try to do is we're going to look at some indefinite integrals. So we start off with some indefinite integral. Here I have like a little example. I have this, yeah? And so basically what we're trying to find is we're trying to find an antiderivative of the inside. That's basically what we're trying to do. And so how are we going to do this? What we're going to want to do is kind of notice here how we have a function in a function, right? We have something like f of g of x, right? So what we're going to want to do is we want to convert this g of x into something a little easier to handle. And so what we're going to want to do is we're just going to replace this g of x with just some letter, u, and see what happens. And so this is basically what we're trying to do here, right? We want to try to handle something easier. So we want to find the antiderivative of u to the 7/9 du. And why do we want to do this? It's because we already know how to do this, right? We know how to take this antiderivative, right? We have one of these functions. And so what we're going to do is let's just try it, right? So let's set u is equal to 3x plus 2. And then in my original formula, so here, up here, here, I'll do this on the side. So I take the integral of 3x plus 2, 7/9 dx, and I replace this inside with u. So this is just equal to u 7/9 dx, right? But now we have a different problem, right? Can you see what the problem is? Think about it for a second and think what might be the problem here. I would even say maybe even pause the video and try to figure it out. Write down here, what is the problem? Okay, so hopefully you tried. If not, I know like it's good to try these things out. You're supposed to be working with these. So what the problem is that here and here we have different variables. We have different variables. Right? We have u, here, I'll do it in different colors. We have u to the 7/9, I guess that's black, d, and our differential is uses a different variable, dx. And so notice how these two are not the same variable. So I can't do this integration, right? And so we're going to have to solve this problem. And the way we're going to solve this is by actually using differentials. And we're going to use implicit differentiation in conjunction, and I guess I didn't write this, in conjunction with differentials. So basically what we do is when I take the derivative, what we're going to do is we take the derivative with respect to x of both sides. So I do d dx u is equal to d dx 3x. Do I want to do this way? No, I don't want to do it this way. What we're going to do, and so we're going to do a slightly different way of doing it, implicit differentiation. And basically what we do is we take the differentiation of one side with respect to u, and the differentiation on the right-hand side with respect to x. So here we kind of get du, right? The derivative of u is just going to be some small change in u. So this is okay. So what we're basically doing here is we're working with differentials, right? So I'm changing u. Instead of being a point, I'm going to make it some small amount, right? And so what's going to happen here, if I want a small amount of x, I'm going to need to multiply it by something, and that's going to be the derivative. So here I would have 3, right? So the derivative of 3x plus 2 is equal to 3. And here we can look at d du of u is just equal to 1. That's why here I kind of have this 1 here. 3 times du, dx, because that's what our differential is going to be. And so here, remember, differentials are actually numbers. So I can divide by things, right? So this implies dx is equal to 3 over, is equal to du over 3. So what does that mean? What this means is, and I do this on the next page. What does this mean? So let me rewrite this out. So we have that, so we said first off that u is equal to 3x plus 2. And then we just showed du is equal to 3 dx, or that dx is equal to du over 3. So what does that mean is here I can actually replace things, right? So here I have the integral. This is just u to the 7/9. And then dx I have as well, right? I know dx, this is just du divided by 3. Okay, now I have the same variable, so I can actually do stuff, bad language. So I have 1/3, so I can bring this 1/3 out. And then I can actually take this, right? I know what the antiderivative is of this, right? So I add 1 to the exponent. So here we would get 16/9. I divide by the new exponent, 16/9. And then remember, we add this plus c. I went over this 6,000 times. Always add this plus c for when we're doing indefinite integrals. And so here I can now multiply, cancel out the 3's to get 3/16. And then here, one thing to note, replace my x, right? So u is equal to 3x plus 2. So I replace in order to find my answer with regards to x, because here I'm asking x, right? With respect to x. So I need to have a final solution that also gives me x. So what did we do? So basically what we did, we have 5 different steps. First step was we made u equal to some function. I guess here I'll use g of x, right? Because we kind of talked about this, right? Making this into f of u. Then what did we do? We did implicit differentiation. Differentiation, right? So this looks like u is equal to g of x. This becomes du, right, is equal to g prime of x dx. Then we replace our variables. So maybe here I should do this up here, integrate, so that we can see what we're doing, dx. So we replace, right? So we replace this is okay. I'll do this here. I'm trying to think at the same time. So I do this. And then so here what we'll do is we replace, right, both of our things. So this becomes f of g of x. We replaced it, so we need to replace this with u. And then dx, this becomes du over g prime of x. And then we do our integrals, So this will give us something, I don't know, something plus c. And then we replace the variables, right? Because here we have something in u. So this has to be equal to something in x. Okay, so that's easier said than done. Let's actually look at an example. I know here I said do it with a partner, but I'm actually going to go over this with you because, I mean, if you want to try it by yourself, test it out. Try it by yourself. And then the thing I'm going to hint at is make this inside your u. So don't worry about the x itself. So actually, yeah, try it out. Pause. Come back in 5 minutes, and we'll talk about this. All right, so hopefully you tried it. So let's actually do this. So I already kind of told you what the u should be. So step 1, right, we said u is equal to 7x squared minus 8. So step 2, we do implicit differentiation, right? So what we do is we take du on the left. On the right, we take the derivative. So this is 14x. The minus 8 goes away. And I'm left with a dx. So what does this mean? I have that dx is equal to du over 14. I can't write. There we go. 14x. And so I said don't worry about the x. So let's replace. So what do we have? We have x times 7x squared minus 8, 16 over 7 dx. And so we're just literally replacing. So we get x we're leaving alone. This becomes u. This becomes 16 over 7 doesn't change. And dx becomes this. So basically what did we do? U, this comes from 1. This, actually I can just do this, is how we get 2. And my u's look like y's today. U. Yeah. So that's part 3. Part 4 is to actually do the integrals. So here, actually, before we move on to part 4, notice what happens here. I can actually cancel these x's. And that's why I said don't worry about it. So here I actually end up getting u to the 16 over 7 divided by 14 du. So we can actually take this definite integral, or indefinite integral, right? So we have 1 over 14 times u to the 16, 7. I add 1 to the exponent. And so I get 23 over 7. Divide by the new exponent. And then what do? I add c. So what is this equal to? This is just 7 over 14 times 23, u to the 23rd 7 plus c. These cancel and I get a 2. So I get u 23 over 7 over 46 plus c. But we're not done. I need to replace the variables. So here I get that this is equal to u, right? So u we have from part 1, that this is equal to 7x squared minus 8 to the 23rd 7 over 46 plus c. Well, that's nice. So this is equal to our derivative, 7x squared minus 8, 16 over 7 dx. So as we see, substitution is very strong for something like this. Okay, so substitution is strong for helping us find antiderivatives, but now let's actually plug this in, right? So the whole point of antiderivatives and indefinite integral is to solve definite integrals. So let's solve a definite integral. So let's do this. So the big problem for substitution, why is it hard? Why is it difficult? It's difficult to notice what you should be. And that is the hard part for this. What should you be? When I look at this, it's a little difficult to see what you should be. And so what I normally like to do is I normally like to take derivatives of things to find when we can cancel things. And so here, if you notice x squared minus x, if I take the derivative, I get 2x minus 1, which is the same thing on top. So I'm kind of thinking that I should make u be equal to x squared minus 2. Minus x, sorry. So what does this give us? This gives us du is equal to 2x minus 1 dx. And so now let's plug this in. So here, we're only talking about indefinite integrals right now. So if we plug this in, we get that, so we have 2x minus 1 over x squared minus x dx. This, when we plug in, we'll get 2x minus 1 over u du over 2x minus 1. So this came from dividing both sides up here. These cancel, so I get du over u. This is just the natural log of u, right? And so now we're going to run into a different problem. So let's plug this in, right? So here, what we had said, oh, because I'm not done. I need to also change this, right? So I get natural log of blah, 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 blah. I need to replace this with 2x, with x squared minus x. Okay, cool. So in this case, this is okay. So what happens when I use these parts? So if I do 2 to the 4, now there's a lot of different things you can kind of do in this case. So some people, what they like to do is kind of do 2 steps at once. So let me first show the original step, kind of how we've learned to do things. So here, how we learn to do things is we first calculate our antiderivative, right? And here I forgot my plus c's. We calculate our antiderivative. And these should have absolute values. And then we can substitute in. But there's a second way we can do this, and that's to combine this and this at the same time. So these together, we can do at once and basically substitute right away. So here what we can do is substitute right away. And people have seen this a few times, and like in other classes, and this is normal as well. But here we have a different problem, right? If I do it this way, I get natural log of u from 2 to 4, right? But notice how these look different, right? Here I'm taking natural log of 4 to 2, and here same, but I'm plugging things in, and that's because the limits are not correct. And so here I have a graph of what this actually looks like when I plot them in one at a time. So this one here, this one is 2x minus 1 over x squared minus x, and this is just natural log of u. This is 1 over x, sorry. Is that right? No. Yeah. Right? Yeah. Yes. And so notice how when I'm trying to calculate from 2 to 4, right? I'm going to get different values depending on which function I get, which function I use, right? This one up here is going to have, here, I'll use blue actually. This one on top is definitely going to have a whole lot more area than if I just do the red part at the bottom, right? So this part has a lot less. And so basically to combat that, what you have to do I have room on the next page? Yeah, so how do we combat this? What we do is we have to keep track of our variables even further. And so here, when I have this is okay. Yeah. What we do is when we substitute, is we have to keep track. There's two things we can do. One is, so we have du u. Remember that u here is x squared minus x. So what we need to do is we need to change these limits. So what do? We just literally plug in to find what their u value should be. So 4 squared minus 4, this gives us 16 minus 4, which is 12. So this top one is going to be 12, right? So this becomes 12. And this comes from this equation here on the right. So how about if I do 2 squared minus 2, this gives me 4 minus 2, which is just 2. So in this bottom case, it actually doesn't change. I still want 2 here on the bottom. So what is this saying? What this is saying is when I take the natural log of u, I can actually plug this in right away. 12 minus natural log of 2. So this is just the natural log of 12 divided by 2, which is natural log of 6. Okay, but there is another way, way of doing this that is also permissible, and that's to keep track of our limits. So what we can do instead is keep track that these are actually for x's and not for u's. Yeah? And so basically what this does is when I plug in my u here, notice how I can't plug these in yet, right? Because here I have a u. So here I have to actually wait to substitute this. And now I can remove. X equals. And from here I can actually plug in. 4 squared minus 4 minus 2 squared minus 2. So here we get 12 minus natural log of 2 is equal to natural log of 6. Yeah? Because notice how basically the calculations here are the same as the ones we did before. So either way, we need to calculate them. And so this is confusing. So if you're looking through this will be on our quizzes /final. So ask questions. If you are confused, stop. Be like, hey, Aram, I don't get it. Email me, Discord me, ask a question. I'm not joking. Ask a question.